Good day, everyone. Welcome to our presentation titled Database Integration. In this part, we will explore the foundational concepts in modern data management. And here are the contents. First, relational versus non relational database. Second, SQL foundation or fundamentals. Third, no SQL essentials or non relational database fundamentals. And lastly, the query techniques.
Hi everyone. Today, we're diving into the world of databases. Specifically, we're going to explore the key differences between relational and non-relational databases. Let's start with relational databases. These are like those super organized filing cabinets. They use tables with rows and columns, and everything has a specific place. This structure ensures that the data is consistent and accurate. The key here is structure. Relational databases use something called a schema, which is like a blueprint for how the data is organized. This ensures data integrity through what are known as ECID properties, or atomicity, consistency, isolation, and durability. Basically, it means your data is reliable. Some popular examples of relational databases include MySQL, PostgreSQL, and Oracle. These are used for things like banking systems, e-commerce platforms, and managing customer orders where accuracy is essential. And now, let's move on to non-relational databases. These are more like that flexible digital workspace. They don't force you to fit everything into a rigid table. This makes them great for handling different types of data that might change frequently. The main advantage of non-relational databases is their flexibility and scalability. They can handle large amounts of data and different types of data without requiring a strict schema. However, they sometimes sacrifice strict consistency for this flexibility. Examples of non-relational databases include MongoDB, Cassandra, and Redis. These are used for things like social media platforms, online gaming, and storing product catalogs where things change rapidly. So, what's the big difference? It boils down to structure versus agility. Relational databases excel in consistency and complex queries, while non-relational databases offer horizontal scalability and flexible schemas. If you need strict data consistency and complex transactions, go with a relational database. If you need to handle large amounts of unstructured data and prioritize flexibility, a non-relational database is the way to go. And now, let's look at a real-world example of a relational database in action. A fruit shop that wants to keep track of its transactions, products, and customers. First, we have the transaction table. This table records each purchase made in the shop. It includes the transaction ID, customer ID, product ID, and purchase date. Next, we have the product table. This table lists all the products available in the shop. It includes the product ID, product name, and price per kilogram. And then finally, we have the customer table. This table stores information about the customers. It includes the customer ID, last name, and first name. The power of a relational database comes from the relationships between these tables. The transaction table uses customer ID and product ID to link each transaction to the specific customer and product involved. We're exploring non-relational databases, also known as NoSQL, which offer a departure from traditional relational models by storing data in formats like column-based, key-value, graph, and document structures. This approach allows for greater flexibility and scalability, making it ideal for handling large volumes of unstructured or semi-structured data. Unlike the relational databases that use tables, NoSQL databases model relationships in diverse ways, catering to modern application needs and providing efficient solutions for complex data management challenges. We're comparing relational and non-relational databases. Two fundamental approaches to data management. Relational databases, with their structured tables and foreign key relationships, offer strong consistency and are ideal for applications requiring complex transactions. In contrast, non-relational databases, also known as NoSQL, provide flexibility and scalability by storing data in various formats like documents or key-value pairs. While relational databases excel in structured environments, non-relational databases shine in handling large volumes of unstructured or semi-structured data, making them suitable for modern, agile application. Number 2. SQL Foundations. Let's dive into core SQL syntax. In set-based thinking, SQL thinks in terms of sets, like groups of data. This is way faster than doing things one by one. Like you have a huge pile of papers, and SQL can sort through them all at once. Like for example, instead of checking each student's grade individually, SQL can find all students with an A+ in one go. And avoid procedural habits. Don't get stuck in old-fashioned, step-by-step thinking. SQL is powerful because it can handle big tasks all at once. For example, instead of telling SQL exactly how to find something, just tell it what you need and it'll figure out the best way to get it. In essential clauses, these are the main commands you will use in SQL. Select, from, where, group by, having, and order by. Think of them as building blocks. In logical execution, SQL runs these commands in a specific order. From, where, group by, having, select, and order by. It's like following a recipe. Alright, let's talk about joins and set operations in SQL. Joins and set operations. Types of joins. Joins are used to combine data from multiple tables. The main types are inner, left, right, and full. In inner join, get only the matching rows from both tables. For example, like you have a list of students and a list of courses. An inner join would give you the students who are actually enrolled in courses. For left join, get all rows from the left table plus matching rows from the right table. If there's no match, you will see null values. For example, you'd get all students, and if they're in a course, you would see the course info. If not, you would see, you still see the students info. For right join, get all rows from the right table, plus matching rows from the left table. For example, you would get all courses, and if there are students enrolled, you would see their info. For full join, get all rows from both tables. In set operations, these are union, intersect, and except. They help combine or filter result sets from different queries. In union, combines the results of two select statements, removing duplicates. For example, you could combine a list of active students with a list of alumni to get a full list of everyone who has ever attended the school. For intersect, get only the rows that are common in both select statements. For example, find students who are both in the math club and the science club. For example, get the rows from the first select statement that are not in the second. For example, find students who are in the math club but not in the science club. Let's move on to the indexes and performance in SQL. Indexes and performance. Index types. Think of indexes like the index in a book. They help SQL find data faster. In B3 indexes, these are like the regular index in a book. They're good for all sorts of searches. Great for almost everything like finding a range of values or doing partial matches. In hash indexes, these are super fast for finding exact matches. Perfect if you need to look up something specific, like a student's ID. In indexing best practices. Index selective columns. Only index columns that you search frequently and that have a lot of different values. Indexing columns with unique values is more efficient. Cover frequent queries. Make sure your indexes cover the columns you're searching on. Avoid over-indexing writes. Too many indexes can slow down when you add or change data. It's like updating the index in a book every time you change a word. For cost-benefit analysis, balancing the cost of indexing with its benefits is crucial. Over-indexing can slow down write operations, while under-indexing can degrade read performance. Finding the right balance is a key.
Good day everyone. My topic is indexes and performance. Indexes are very important in databases because they help speed up the searching and retrieval of data. They work like a shortcut instead of checking every record. The database uses an index to quickly find the information you need. First, index types. There are two common types of indexes. First, the B3 index, which is best for range searches, like finding numbers or dates between two values. Second, the hash index, which is used for exact matches, for example, searching for one specific ID or name. So, indexing best practices. When using indexes, it's important to choose the right columns, usually the ones that are searched most often. But we should not add too many indexes because that can slow down updates and data changes. The goal is to keep the database fast and balanced. Last, cost-benefit analysis. Indexes have both advantages and disadvantages. They make reading data faster, but they can make writing or updating slower. That's why we need to balance how many indexes we use depending on the needs of the database. Before I end my report, I want to emphasize that indexes and performance play a big role in making databases work efficiently. Indexes help speed up data searching and make system run smoother, but they must be used wisely to keep everything. Overall, my report shows how proper indexing can improve database performance and make data management faster and more effective.
Content 3, NoSQL taxonomy. First, key-value stores. Key-value stores like Redis provide fast access to data using keys. They are ideal for caching and season management. So, key-value stores sama sa Redis kay isa ka database nga nag-store og data gamit ang key og value. Ang key kay unique names para makuha ang value. Basta siya mo access sa data, mao na gamit kaayo para sa caching og season management sa mga web apps. Second, web column stores. Web column stores like Cassandra are designed for large volumes of data, flexible schemas. They are suitable for time series data. So, wide column stores, isa yun sa databases nga kaya mo handle ng daghan data o flexible pagod ang structure niya. Dili pareha sa traditional databases nga fix ang format. Dire sa wide column stores pwede ka magdugang ng columns anytime. Usually, gigamit ni siya para sa mga time series data. Sama sa records sa temperature, user activity, o sensor data. Kaya dali ra niya ma-store o ma-retrieve ang bisan daghan kaayo mga entries. Mao ni nga ideal siya ideal siya para sa mga system nga nag-process og large scale data everyday. Third, document stores. Document stores like MongoDB store data in flexible document formats. They are ideal for product catalogs and content management systems. So ini na database gana ni siya gamiton para sa mga product catalogs o mga content management systems. Kay dali ra i-update o i-organize ang data bisan dahilahi ang format sa matag documents. In short, flexible o efficient siya para sa mga application na nag-handle og dynamic content. Fourth, graph database. Databases like the Neo4j are optimized for relationships between data. They are perfect for social networks and recommendation engines. Graph databases is siya ka database nga nag-focus sa relationship between data. Dili lang siya nag-store sa data mismo, pero kung unang connection sa isa ka data ngadto sa lain. Kaani na siya, perfect na siya para sa social networks, sama sa pag-track kung sino ang friend or followers nimo, o great mga recommendation engines, mga movie or mga product suggestions. Kaya dali ra niya matrace o ma-analyze ang mga connections. In short, graph databases kay para sa data nga interconnected or nagdepend sa relationships. Cap and base explain. First, cap theorem. Cap theorem states that a contribute system can only guarantee two of the three properties: consistency, availability, and partition tolerance. This trade-off is fundamental in SQL design. So, ang cap theorem isa ini siya ka distributed system. Dili mo makuha ang tulo ka properties sabay-sabay, ang consistency, availability, and partition tolerance. Pwede ra duha or tulo ang ma-achieve at once. Example, kung gusto ka nga consistent og available imong data, bisan dili siya tolerant sa network partition, mao ni nga importante kaayo na concept sa no SQL design, kay magdepende ang system sa unsa nga duha sa tulo ang importante para sa imong application.
Content number 3. Cap and base explained. Second is base semantic. Base stand for basically available, soft state, and eventual consistency. It allows system to be highly available and scalable at the cost of temporary inconsistency. When we say basically available, it means system still works most of the time. And soft state, it means data might not be immediately updated everywhere. And also, eventual consistency, it means all parts will match later. For example, you like a post on social media, it might not show the updated like count instantly for everyone, but after a few seconds, it becomes the same for all. Third is practical examples. Eventual consistency is seen in shopping carts and social likes, where immediate consistency is less critical. This approach ensures high availability and scalability. When we see practical examples, it means base systems are used where instant accuracy isn't critical but speed and uptime area. For example, shopping carts. If you add an item, it appears after a short delay. And just like or comment, the count updates a bit later to everyone. Next is schema flexibility. First is flexible schema. Documents stores allow embedding evolving attributes without costly migration. This flexibility is crucial for application with changing data requirements. Flexible schema, it means the database structure can change easily. You can add new fields or data types anytime without breaking things. For example, a user profile start with your name and email. Later, later you add profile picture or hobbies. No need to rebuild the whole database. Second is versioning and validation. Versioning, versioning strategies and validation rules prevent chaos and flexible schemas. They ensure data quality while maintaining agility and continuous deployment pipelines. Versioning validation, it means keep track of changes and check the new data still fits the role so updates don't break anything. For example, if your app updates the store user age versioning, ensure all data without age still works, and validation check the age is a number, not text.
Good day, everyone. My name is Maria May Sanchez, and my discussion is all about advanced SQL patterns. Advanced SQL patterns has a different patterns, which is the three different patterns. Um, Number one is window functions, and number two is CTS, which is common table expressions, and the three is recursive queries. Number one is window function is allow calculation across a set of rows, such as ranking and running to tails. They simplify complex queries and improve performance. And number two is common table expressions. CTS provide a way to define temporary result sets that can be reused within a query. They improve reliability and maintainability. And the last thing is recursive queries, which is solve hierarchical data problems like a bill of materials explosions. They replace complex and procedural code with concise SQL. And also, let me share with you the topic of new SQL query models. They have four query models, which is number one is K lookups, and the second is secondary and indexes, and the three aggregation pipelines, and the four is graph traversals. Okay, let's start from the K lookups. K lookups are the fastest way to retrieve data in K value stores. They provide instant access to data using unique keys. Okay, the second is the secondary indexes. Secondary indexes allow queuing on non-K attributes. They are essential for flexible querying and wide column and documents stores. And the number three is aggregation pipelines. In document store like MongoDB allow complex data processing and transformation in single query. And the last but not the least Number 4 is graph traversals. Graph traversals in graph databases explore relationships between nodes. They are powerful for querying complex networks. That's
For our report, I will discuss the polyglot representance. Polyglot representance means using different types of databases, relational and NoSQL, within a single system depending on your specific needs. So, for example, pwede ka magamit ng MySQL para sa user data o MongoDB para sa logs o sa messages. Then, the pattern for coexistence. Patterns like CQRS, event sourcing, and change data capture enable seamless integration of relational and NoSQL databases. They ensure data consistency across system. So, for example, sa isa ka online shopping app, ang product info pwede na sa is NoSQL kay para flexible. Pero, ang origin story of payments nasa relational database. Then, ang change data capture mag-update sa line database. Kung na bag of order para pareho silang updated. So, ang second is operational considerations. Consistency, window, idempotent, consumers, and monitoring tools are crucial for reliable polyglot persistence. They help manage complexity and integrated system. For example, kung ang isa ka order ma-save o balik tungod kay ang network delay, ang system mag-check na dili ma-record og duha kay parehas ang order. Amoy ni ang idempotent consumer. So last, this is the recap or key takeaways. So, model data to queries, index consciously, embrace eventual consistency where acceptable, automate schema migrations, and monitor across engines. This practice ensure effective database integration. So, here's the example or explanations. So, ang model data to queries, i-design ang imong database base sa klase ng pangutana na permi nimo gamiton. For example, kung permi ka mangita og user by location, dapat na kay index sa location column. Then ang embrace eventual consistency. Example, di kinahanglan ng instant pareho tanan data sa tanan databases basta moabot sa parehas nga result after the short time. Then example, kung ang user info updated sa MySQL pero mo delay gamay sa MongoDB. Okay na basta eventually pagkapareho da. So sa automate schema migration, kung naay changes sa database structure, gamitin ng automation tools aron di manual mag-update. So, ang monitor across engines, bantay ang performance o status sa tanan nimo nga databases. So, here's the con. So, ang polyglot persistence means using different types of databases together to achieve the best performance and flexibility. Napasabot ini nga mag-mix of relational o NoSQL databases depende sa atong kinahanglan. Pero ang importante nga naay madayaw na pattern o monitoring tools para magpabilin ang consistent o synchronize ang data bisan lain-lain ang gigamit nga system. So sa best practice, remind us to model data properly based on the queries we often use. So, add index para mas fast ang access sa data. So, accept small delays kung okay ra ang eventual consistency. Kinahanglan nato na i-automate ang schema updates para dili ma-manage ang changes o bantayan permi ang system performance aron malikayan ang error o downtime.